All right, what up, fam? My favorite math proof part number 2. We're going to show that the size, remember that's what these bars mean when you're talking about a set, the size of the numbers that are in between 0 and 1, and I'm really talking about the real numbers here, by the way. There's actually a harder proof that kind of shows that the real numbers are 1 to 1 with 0 to 1, but that's a whole other thing. The real numbers here from 0 to 1 are much, much bigger than the size of the naturals. And the reason why this is so dang surprising is we showed in our previous video there that the size of the naturals was in fact equal to the size of the integers, that they're the exact same thing. But it turns out if you add in the decimal numbers, and that's all you do is you add in every single possible decimal number, including those irrational numbers, then well, it's not. So let's go through this proof. And again, it's more like a proof outline, not a formalized proof. And this is going to be what's called proof by contradiction. So you're going to instead assume that they're equal. And if you assume that they're equal, what that means is I can start naming them off, and I can simply put them into a list. And I can say, maybe my very first one, I'm going to label it A sub 1. My very first decimal number is 0.123, 123, 123, 123, so on and so forth. That is my very first number I've decided. And I'm going to go ahead and decide that my second number is 0.145962. I forgot the rest of what pi is. I'm going to keep on going on there, but that's actually just pi minus 3. That's our second one there. And then our third one here, I'm actually going to need, in order to make this argument, I'm going to need at least 4 numbers to kind of make my point. So that's what we're going to be doing here. Get 4 numbers. How about we get another one? How about let's do 71828 dot dot dot. There you go. We got e minus 2. And how about another one? 0.693214. We got the ln of 2 coming on in here. And the point is that I am able to do this because I'm saying it's the first one, which lines up with the first number of the naturals, or 0 if you really wanted to. 2 lines up with 1, 3 lines with 2, 4 lines, and so on and so forth, that they line up with each other. And we showed this, that this is 1-to-1 correspondence. So sure enough, this list that I have made must have a 1-to-1 correspondence with those natural numbers. But now I'm going to go ahead and say I'm going to create a different number. And I'm going to create this number where I'm going to say this number here, if that, what the number is going to do is it's going to be created using all of the other numbers. It's simply going to say, in the event that the very first number in the first, if the first number's first decimal place is, if this guy is a 5, then this is also a 5. But if it's not a 5, then it'll be some other, actually, let's pick a 4 instead. Sorry, we're gonna do 4. So in saying if 4, then 4, if not, then 9. So for instance, the very first number here, this 0.1, well, that's not a 4, so I'm gonna label it a 9. And then in the second number, right there, it is a 4, so I'm gonna label it a 4. And then the third number is right there, it's 0.8, so it's not a 4, so I'm going to call it a 9. And then the fourth number, I'm going to go to the fourth one over here, and that's a 2. And this is actually going to continue on forever, because remember, I'm going to use up every single number in my entire list. But I created this number by using the other numbers. And therefore, for instance, where would this number be on my list? Because it can't possibly be anywhere if it was created using a rule where it had to match that first digit. And the idea is that this is called a diagonal argument. We take the first and the first, the second and the second, the third and the third, the fourth and the fourth. And if you always do that, you're going to end up creating an additional number that is not within our list. So what have we done? I have created this number b, that is decimal number, that is certainly in between 0 and 1. Absolutely, it's in between 0 and 1, but B is not within my list. That was off the entire thing. And therefore, we have a contradiction. and then we have a contradiction and we say, therefore, it must be the case that this guy is bigger. And it's infinitely bigger because I only use the first number in the first position. I could have also used the second number of the first one and the third number of the second one, and so on and so forth. I could have always simply used an additional number. And because of that, it must be the case that this infinity bigger than this one. I'm done with the video. Have a great rest of your day.